So I'm very happy to present today Dr. Partha Roop from the Department of Electrical and Computer Engineering. So Partha has a BTech and an MTech from India, from the Anna University of Engineering and IIT Kharagpur. Then did a PhD in Computer Science and Engineering from New South Wales, and has been at Auckland for a number of years now. So Partha has his interests are in formal methods and in cyberphysical systems, and he's been developed collaborations with the ABI over a number of years in these areas. So he's going to be talking to us about some of his work in that area.
Thank you, Vinod. Thank you so much, and thanks for coming along. So this is obviously not my own work alone. This is work of a number of colleagues and students. So in particular, Nathan Wewe, both of whom are here. Siddharth Andlam, who is now an academic in NTU. Eugene Ip, who teaches in Germany. Tony, who initiated the work on pacemakers, about which I will present a little bit today. Colleagues Avinash Malik, Mark True, Nitish Patel, and a colleague from IIT Bhubaneswar and a student with whom I did some recent work on pacemaker security. So please stop me at any time. This can be an interactive presentation. So how it got started, I never thought I'll work on biology until there was this ideas workshop. I was working on pacemakers, but that's it. I mean, just pacemakers. And if I came and presented some pacemaker design to you guys at ABI, you would just laugh at me. So anyway, coincidentally, there was this ideas day. I think it was 2013. And Bryony James and Chris Ford were organizing this, and I went along, and Martin Nash was there, and we got talking. Then I invited Martin to a presentation by Tony, and there he introduced me to Mark True, and the rest is essentially my talk. So work was initiated through a FRDF funded project called Heart-on-FPGA. We started in January 2014. I must say that like our work that I will be presenting today, there are many global initiatives. Like one project in particular is a National Science Foundation project from the US, and this project is called Cybercardia, where this is an initiative led by Stony Brook University, and I'll present our cardiac cell model, which is sort of a modification of the Stony Brook cell model. And then Cybercardia has people from University of Pennsylvania and CMU and University of Maryland. So it's a really a project spanning some top universities in the US. And like that, Professor Martha, I don't know how to pronounce the last name, her group, and I think we visited her in the past. She had a number of EU-funded projects looking at similar problems to what I'm going to present today. So by no means what I'm presenting today is just the work that is happening at Auckland, but other people are also looking at similar sort of approaches. So kind of an overview of kind of my research area. I work in this area called Cyberphysical systems, where you use computers to control physical processes, and they can range from examples in transportation like autonomous vehicles and their interaction with the traffic control algorithms, all the way to medical devices. So in this talk, I'll focus on medical devices, and basically when we talk about medical devices, there are a lot of pacemakers. This data may be even a bit dated. So this data is from this paper from the University of Pennsylvania group that I was talking to you in the previous slide. And they say that excess of 10 million pacemakers used worldwide, but between 1990 and 2000, 41% of these are recall pacemakers and ICD devices. And they point to firmware issues being the causes for these recalls. And and there is a more recent study which is published in 2013. And in this study, if you see that these recalls are not going away. They are in fact increasing. And what is intriguing is this axis is in thousands, and these are number of adverse events. And if you look at the number of adverse events, it's pretty large in 2011, including a large number of deaths, and that's not very good. When we are designing implantable medical devices to treat some kind of medical conditions, we need to make sure that they are indeed used for helping out the patient. Now, the other issue is that of recalls. Now, when, for example, my Toyota car had a recall of some component, that is to some degree difficult. You have to give your car away. But when a pacemaker is recalled, then it has a lot of other implications, which we all understand. So, a little bit about the pacemaker context that I will be talking about. And in this particular diagram, I'm talking about the DDD mode pacemaker, which is a dual chamber pacemaker, where this is a typical example of a cyberphysical system where the pacemaker is sensing both chambers of the heart, and we can think about two digital inputs coming to the pacemaker, the atrium sense signal and the ventricular sense signal. And the pacemaker acts as a controller which is generating two outputs, atrium pace and ventricular pace. I will give some more details and some more timing diagrams later. But this is an example of a closed loop cyberphysical system, somewhat simplistic, because in cyberphysical systems there is also the notion of distribution of these controllers. In this case, the controller is centralized. But the interesting thing is, still, this device, which we might consider to be somewhat simplistic, has been a cause of concern, like the previous slide. And also, more recently, there is a 2017 report that over 400,000 pacemakers were vulnerable to hacking, that hackers could either drain the battery or could pace so rapidly that the patient can die. So there is problem with respect to safety, and there are problems with respect to security, and I am going to touch upon both these problems, time permitting, in this talk. So when we talk about kind of safety of devices or safety of cyber components, we can take some inspiration from aviation, and already people in medicine are doing that. For example, this is a famous surgeon from Harvard University who proposed this idea of a simple checklist when critical surgeries are done, or when critical care happens in the ICU. So Atul Gawande's checklist manifesto has been adopted all over the world by simple checklists which he introduced in medicine, inspired by aviation, inspired by what happens at Boeing. He says that many lives can be saved, and this is already adopted worldwide. Likewise, when we deal with kind of cyber components in for example, airplanes, the code in the airplane, if it doesn't work as desired, there are obvious implications. So what typically happens is that the code in airplanes are developed using some kind of rigorous mathematically founded techniques, and one tool is by a company called Astral Technologies, now ANSYS, and the tool is called SCADE. And SCADE is a kind of a graphical programming language like MATLAB Simulink, very similar to Simulink. But the difference between SCADE and Simulink is that in SCADE, once you do your design and you are satisfied with your design, it automatically generates C code. Simulink also does that. However, the SCADE compiler automatically generates code that is certifiable according to this standard. So to my knowledge, it is the only certifiable compiler in the world. Now, this approach is founded on formal methods, and I will elaborate more what I mean by formal methods subsequently. Now, I wonder if we are increasing the reliability of airplanes, automotive software using these techniques. Why can't these techniques also be used as we design safety critical systems in the medical domain? So that's kind of a question that I would like to pose, and then I will start off by giving a short demo of the system that the algorithms that we are going to talk subsequently, and this system, which is designed by one of my PhD student, Nathan Allen, who has recently 3D printed a heart. And then obviously this looks simplistic, but to create this, the wiring and all that, and for the LEDs is non-trivial. He must have spent a lot of time doing that. Now, what we have got is kind of an interface circuitry to a heart on a chip, which is executing on this FPGA device. And actually, even though this is an FPGA, there is a ARM-based processor on which we are generating code. And this code is essentially trying to mimic the electrical conduction system of the heart. And currently, the pacemaker is turned off. So we have got 2 leads going into this Medtronic pacemaker we have received thanks to Mark from the medical school. And currently the pacemaker is turned off. And what we can do is, because this is a mathematical model-based design, we can parameterize the system and induce different kinds of failures, different kinds of arrhythmias. For example, what I can do, and just by flicking a switch on this board, I can induce, for example, AV conduction problems. And then you will notice that the behavior of the heart changes. Likewise, I can, for example, induce SA node failure. So SA node is not beating, and the other pacemaking regions like the AV node are now triggering the kind of conduction, and so on and so forth. And what we can do is now to see how the pacemaker will kind of offer some treatment for different kind of diseases. We can connect the pacemaker back. You will now notice that in spite of the AV conduction, the pacemaker is bringing back normal behavior, and I can induce other kinds of arrhythmias too. And after some time, the heart should beat normally. So, so this is the kind of system that we are proposing, that when we are testing cyberphysical medical devices, before we want to trial these devices on humans, can we have a different approach to designing these systems, and can we test these systems more rigorously? Any questions until this point? So that brings me to this main theme of my talk, which is what exactly is formal methods. So formal methods are a collection of techniques which initially emerged thanks to the work of some researchers with US military, and subsequently they have been adopted a lot in safety critical systems in aviation. So these are kind of, so I'm referring to a meta survey in ACM computing surveys, a recent survey, 2009 survey. To my knowledge, this is one of the most recent survey of surveys. And it's a very good broad spectrum view of kind of how formal methods has emerged from techniques which are purely very simplistic to techniques which are now applied to industry strength problems. So what are they? These are mathematically founded techniques for developing software and hardware. These were initially used primarily in hardware, for example, when the Intel Pentium bug was detected by a mathematician, a model checker actually found the path to the actual error in the Intel processor, in the floating point unit. So mathematical rigor enables users to analyze and verify these models at any part of the program lifecycle. So you can use formal methods starting from all the way from specification to implementation in different stages of the life cycle of the design. So techniques encompass those founded on mathematical logics, process algebras, programming language semantics, and automated proof techniques. These have got immense impact in the domain of computer science. Like the field medal in physics or the Nobel Prize in other disciplines, the Turing Award is kind of the maximum recognition for work in computer science. So these are, I've listed the major Turing awardees in formal methods, like the latest one is 2013 Leslie Lamport, who has done foundational work on real-time systems. He defined the concept of safety and liveness that formal method researchers routinely use. Edmund Clark, Syphakis, and Immersion independently developed. Clark and Immersion in US and Syphakis invented this automatic algorithmic technique independently. They did not know each other's work, but the techniques are identical. This is known as model checking. This is being used to verify large programs. In 2012, people verified 10,000 line C code automatically using model checking. And prior to that, large hardware, for example, in 1990s, one of Edmund Clark's students, Kenneth Macmillan, in his PhD thesis, he published a paper called Verifying 10 Power 20 States and Beyond. This is 1990s. So, so applications to hardware has been immense, but applications to software is also becoming increasing. And then Amir Pinwelly discovered the link between temporal logics invented by philosophers back into the safety verification of complex hardware software systems, 1996. Prior to that, Robin Miller and Tony Hoare in the UK developed the concept of process algebras to mathematically represent complex concurrent systems. And they both got Turing Awards at different times. So what I am proposing in this talk is kind of borrowing from this large body of work in formal methods, and can we apply this in applications in biomedical engineering. To do that, what I'm proposing is that maybe we can rethink how we traditionally validate these medical devices. So possibly we validate medical devices in open loop by simulation, where essentially we stimulate the system, we observe the response, and we see if the response is as desired. And then what I would call the next level would be emulation, where you validate the device in closed loop with an actual organ. Like, for example, what happens at ABI, you perform animal experiments, or maybe pacemaker companies might be also doing that. But what we are proposing is a step between this and clinical trials, where we can use kind of emulation models using synthetic organs like the ones we are discussing in this lecture, where we can put this synthetic organ in closed loop, provided this organ, synthetic organ can drive this device in real time and get response like a live organ. So if we can do that, then we can validate this more rigorously. Now, the next part of my talk will go into details of how we design such a system and how to make it such that the synthetic organ provides a real-time response like a live organ. To do that, we have to consider two key facets of formal methods. One facet of formal method is known as abstraction, where you have a concrete system, which is the actual organ in question, which might have millions of cardiac cells and many conduction pathways. But using abstraction, we can abstract this system into a more abstract system which still exhibits the biophysical phenomena that the concrete system exhibits. Can we do that? So by abstraction, we might be able to gain some efficiency, but if we cannot elicit the biophysical phenomena at the concrete level, then this abstraction is meaningless. So we must abstract in a way that we can preserve the biophysical phenomena at the lower level. Now, what we did is I apologize for the slide, but basically what this slide is showing is that the cardiac action potential of a given cardiac myocyte or a pacemaker cell can be represented as an automaton like this, which is known as a hybrid automata. And what this hybrid automata is doing is, instead of modeling exactly the different ionic currents like you typically do in cell ML, you only model the voltage of the cell as you stimulate the cell. So initially the cell is resting, then if you stimulate it above a particular threshold, then it gets stimulated, then it goes into ERP and RRP and goes back to resting. This can be mimicked using ODEs that exhibit this continuous phenomena in each location, and some kind of discontinuities which happen when a transition triggers. And you go to a different location, again ODEs help in calculating the voltage in that particular location, and then so on until another transition triggers. So this kind of automaton is much more abstract compared to the detailed biophysical models that bioengineers use. So obviously when you abstract, you are going to lose something. But what we show is that in spite of this abstraction, we can mimic some of the key biophysical phenomena that are essential to mimic kind of the behavior of the cardiac conduction system faithfully, so that we can still use this in validating pacemakers. For example, here you can see that this system is not a closed system. The cell is responding to stimulus from adjoining neighboring cells, and if you trigger it during the RRP period, you will have a kind of an action potential where the APD duration is short and the voltage is also reduced. And you can then see stimulation starting from say 160 millisecond until 300 millisecond, and how this kind of cell responds to stimulation over time. So this dynamic behavior of secondary excitation can be captured by this more abstract model, similar to low-level models. Wei did some further work, and here is the action potential of a ventricular cell, and Wei shows that the restitution behavior pretty much mimics the restitution behavior of human ventricular cells, more or less, almost with some slight divergence. As you increase the diastolic interval, the behavior essentially mimics a human ventricular cell's restitution. So that is one kind of interesting result that these abstract models exhibit. Also, another interesting behavior that Nathan also finds in his model is that of spirals, that which I'm not presenting, but we can also mimic the behavior of spirals that you typically see, can be also mimicked in our models. And the conduction system that I presented in that demo is essentially a conduction network consisting of a network of cardiac myocytes which are represented in, let me see. So the red are the pacemaker cells, the orange are subsidiary cells, and the blue are the cardiac myocytes. So this is a conduction network of cardiac cells of different types represented as hybrid automaton, and the conduction delay between them is abstracted away. Instead of modeling many cells in between, we abstract these into kind of just modeling the time delay to pass the conduction either in forward direction or in backward direction. So we can mimic both forward conduction and backward conduction. Also, we can model kind of re-entrant circuit by having both fast path and slow path in this conduction network, so that we can mimic the re-entrant behavior which happens as cardiac diseases happen. So, so this network is an abstraction of the conduction system which can mimic different kinds of cardiac diseases. Now, in order to mimic the conduction from one cell to another cell, we use the concept of a special type of hybrid automaton, which is known as a timed automata, where the only continuous phenomena you can model is time. So other types of continuous phenomena are all abstracted away, and the only continuous phenomena you can model is the progression of time. Now this is what is known as a path automaton, and in this automaton you will see the symmetry. Basically we can model conduction from any node I to node J, or in the opposite direction from node J to node I. And essentially what the path automaton is doing, it is either mimicking the pathway into a wait state, and this essentially models the conduction delay, and after which it will relay the voltage to the neighboring cell. So you can model this using the concept of timed automaton. So we have a network of essentially a network of hybrid automata and timed automaton to model the conduction delay between the different nodes. And these models are what are known as formal models. So not only these models enable kind of automatic code generation so that we can perform emulation, they also enable some kind of static analysis. We can also analyze these models and determine some properties about these models. I will show you another demo shortly about the formal verification aspect. So now how do we generate code? So what is the methodology that we followed to automatically generate code from these models? So basically the models have some ODEs of this form. So we had actually 3 ODEs. I apologize for the quality of the projection, but essentially we have Vx, Vy, Vz and an algebraic equation. So this is an ODE DAE combination system, and each ODE can be correspondingly discretized using standard numerical integration techniques. For example, using forward Euler or using Runge-Kutta, order k, or any other numerical integration technique could be used to discretize this, where delta is the step size of the integration, and this is very well known. But what we do in our technique is I borrow the idea from synchronous programming, and we essentially discretize the execution of the different automatons in my system. And using such discretization, what I can do is a hybrid automata can be mapped to a standard finite state machine, and the mapping is kind of very intuitive. So for example, the 4 locations are mapped to 4 states, Q0, Q1, so on and so forth. And these locations have ODEs. Now we have removed those ODEs, and what we do is when execution remains in a given location, we have self transitions, and these transition trigger relative to ticks of a global clock, like in synchronous programs. So essentially every tick, which is the delta step, you essentially solve the ODEs and update the value of the variables until one of the outgoing guard conditions is true, and then you take the corresponding transition, and then you will evolve the variables according to the ODEs that are defined in that location. So we can translate each automaton, each hybrid automata into a discrete finite state machine from which generating C code is reasonably straightforward. So essentially then what we do is for every FSM we create a structure and a series of functions for each FSM. For example, there is an initialization function and kind of a run function which mimics the actual behavior of the given finite state machine. And the structure essentially defines all the variables that we need in that particular FSM. And in order to actually execute a network of FSMs, what we do is we execute them synchronously. So what is the idea of synchronous execution? In order to explain that, I think I'll pause for a minute and I will see if I have a interesting digression. So this is three very well-known, oh, I'm sorry. I need Wi-Fi. I think I don't have Wi-Fi. Oops. Give me a second. I think Wi-Fi was switched off because of which.
This is not a very interesting digression.
Yes. I'm sorry, my mistake. What I did is I had the Wi-Fi off, and yeah.
It's not a very good look for fault-tolerant systems either.
Well, I'm not claiming that my Mac is fault tolerant.
You're not getting Wi-Fi.
No, I'm getting Wi-Fi, but I'm just, I think I will, because I lost time, I will skip that. I'll just continue. Okay, sorry about that. I wanted to actually show three Indian classical musicians in a concert where they are synchronizing in real time. And this is kind of a metaphor for synchronous programming, where essentially programming threads synchronize based on the concept of a logical time. Indian classical musicians, when they synchronize in a concert, there is no conductor performing the synchronization. They synchronize using the beats of a tabla player, which I wanted to show. My apologies. But essentially, same concept is used in a synchronous program where essentially you can have many concurrent threads, and these threads come together in harmony based on ticks of a logical global clock. And we use the same concept as we generate code for the cardiac conduction system. For each node in this hybrid automaton, it's kind of beating away at its own rate, but they are all synchronized based on the ticks of a logical clock. So how we do that is essentially all these concurrent threads are compiled away to produce sequential code where at the start of the tick, you update the inputs, you invoke these FSMs in any arbitrary order you like. These FSMs execute in their own arbitrary order. They may be communicating, exchanging data, but this communication and exchange of data happens based on the value of variables in the previous instant of time. So they can be composed seamlessly. So you can execute this FSMs in some cyclic order, then update the outputs, and you go back and complete this loop. And this kind of defines the worst case response time of the cardiac conduction system. And as long as you can determine this worst case response time statically, which we can do on kind of embedded processors, then you can compute that relative to this worst case response time, whether you can respond fast enough or not for a medical device like a pacemaker. So that is the essential idea. And based on this, we generated code in our compiler, which is known as PIHA, without optimization and with optimization. And in addition to the cardiac conduction system, we compared the performance of PIHA relative to many other different hybrid automata-based implementations of cyberphysical systems. And we found that PIHA can generate quite efficient code even when compared to tools like Simulink. For the conduction system of the heart, the kind of results we got is sometimes over 2 orders of magnitude faster. But more importantly, the compiler generates kind of scalable code, which is much, much more scalable than Simulink. For example, Simulink, after about 300 or so nodes, it essentially runs out of memory. Whereas for PIHA, we can scale to much larger number of nodes. So not only it is very, very efficient, so 5 times more scalable, but it is also quite scalable with respect to the number of nodes of the conduction system. So while in this case I showed you only 44 nodes in the conduction system and the code generation for that, in theory we can generate much higher resolution cardiac conduction system. So now I will give a demo about a slightly different kind of application of formal methods using a tool called UPAL, where we will try and see how to kind of use this kind of technology for verifying if the system is working as desired. So UPAL is a software technology for formal verification. So what I will do is I will now open a system which is pre-designed. So not this. So this is my PhD, master student Tony Zhao's work about 4 years ago. And in UPAL, what I can do is I can open this automaton and perform formal verification. So here is a system for kind of formal analysis of safety critical systems, not necessarily just pacemakers. You can define any system. And unlike the synchronous concurrency there, here this system consists of many concurrent components. So if we go to the simulator, so this system comprises of many different automatons for a DDD mode pacemaker, which is a closed loop system which consists of a kind of a heart model, and this model is a timed automaton model which is composed with all the different timers in the pacemaker which are also modeled as timed automaton. And then what you can do is you could obviously simulate this system, but more interestingly, you could perform a formal verification. So what I will do is I will obtain a query file which represents a kind of a set of properties that this system needs to satisfy for its soundness, for its correctness. For example, one simplistic property we can check when we have so many automatons operating concurrently, is there a deadlock possibility? So I can check if there is no deadlock in my system. So this is a temporal logic formula which is saying AG along all paths globally, there is no deadlock. And let's try and check that. Now this property has passed, so the model checker is saying that for this system, for the DDD mode pacemaker, there is no deadlock in my system. The system is deadlock free. Likewise, I can also check some temporal property. For example, I can check that my LRI time interval is always respected by this pacemaker. So the pacemakers have different kinds of timers, and LRI is the lower rate interval, which is a kind of timeout period that the pacemaker has to respect. So let's see and check that. And here I'm getting a error that my system is not meeting the LRI timeout period that the pacemaker needs to respect. So using this kind of temporal logic based model checking technique, you can statically analyze the system, and when a property fails, it will actually give me a trace that I can play and find out exactly where the bug lies in my large composition of several automata. So, so timed automata-based verification is a very interesting avenue, I think, for medical devices research. So for example, using a timed automaton, I could abstractly represent the behavior of a heart as a random heart just using a single location timed automaton, which is modeling a random ventricle which is beating randomly between two time intervals, some minimum interval and some maximum interval. And this can be modeled using so-called clocks. So here what I do is I have an invariant in this location which is saying that a real valued clock variable is less than some maximum time, and I can delay in this maximum time until this invariant holds, as long as this invariant holds. And before this becomes false, either this guard or this guard has to be true. So what this is mimicking is a randomly beating heart where the clock is moving uniformly until one of the transition triggers, the clock is reset, then again it is again respecting the beating between these two timing intervals. So this is an example of abstractly modeling, much more abstractly than the previous models, the behavior of a heart as a timed automaton. And then what you can do is you can compose a network of such timed automata and you can perform verification like the demo I said. So the last few slides of my presentation is about pacemaker vulnerabilities and pacemaker security problems. So turns out that many IMD devices are actually vulnerable to attacks because they use some kind of Wi-Fi like protocols for communication. So the key problem is the trade-off between allowing emergency device access to healthcare professionals while ensuring that device prevents unauthorized access. So this is a very, very interesting problem. How do we ensure that we can give access to healthcare professionals, because standard approaches to making things secure is encryption? Then this problems comes back. So what people are thinking of is some techniques where we can monitor these devices using additional monitoring devices which ensure security. And there are some interesting new works in this where people propose these monitoring devices which snoop all wireless transactions to see if there is a potential for any kind of attack. But this introduces kind of additional problems. Sorry, why is that? Oops. So what we did instead is that we said, let's see if we can kind of make the pacemakers more secure without having additional devices, because these will have to be certified. Can we make it more secure? For example, on an Apple Watch Series 4, we have an app, and by just having an additional app which does some analysis, does some formal methods, does some formal analysis, we can ensure that the device can detect if a pacemaker hack has happened or not. So this is the typical timing diagram of a pacemaker. For example, the pacemaker is having different timers, and it is monitoring the time interval between different events. For example, there is an interval known as atrioventricular interval, which is the maximum time separation between an atrium sense and a ventricular sense. In this case, the ventricular sense happens before the deadline, so that is fine. But in this case, after the atrium sense, AVI has expired, ventricular sense hasn't happened, so the pacemaker is pacing the heart. So this is kind of typical timing that the pacemaker is monitoring. So can we now use this to enforce some kind of security? So what we decided to do is that we said we do not want to alter any logic in the pacemaker. The ECG is already available as a body surface measurement, and we can infer some of these timings by analyzing the and performing peak detection in the ECG. For example, we can have a set of formal properties P1 to P5. For example, property P5 says R wave must arrive within the PR interval after the P wave. Likewise, P4 says after an R wave, another R wave cannot come after the RP interval. These properties correspond to the corresponding timing properties of the pacemaker. Then what we did is we have kind of an approach using formal methods where we do ECG signal processing, and then this extract the timing events which are passed into a runtime monitor, which can be implemented as an app on an Apple Watch or similar device, which provides verdicts. The essential idea is that the pacemaker timing parameters are programmed simultaneously on the monitoring device and the pacemaker. So the physician who programs the timing parameters of the pacemaker can also program the app with identical timing parameters. The wearable device monitors familiar ECG to ensure that these have no hacks. In the event of any timing violation, an alarm can be sounded. So, for example, a policy that that we want to monitor can be formally captured using a timed automaton like this. For example, one policy could be the policy P4 we talked about, where essentially, as long as the R event is not detected, I keep on looping in L0 and keep on accepting the input. So these double circles indicate accepting states in the timed automaton. Whenever I detect an R event, I initialize a clock variable to zeros, and then the clock ticks. And if I get an event which is other than the R event, I still accept it. If I detect an R before the RP interval, I go into a violation state. So all I'm saying here is that using a timed automaton, I'm monitoring if the time interval between two R events is less than the RP interval or greater than the RP interval. If it is less than the RP interval, it's a violation. If it is greater than the RP interval, then I accept it. So then what I can do is I can essentially perform some kind of formal analysis over traces. Instead of analyzing the whole system, I'm looking at the current trace. The trace is essentially a timed event like this. At 300p happened, at 208R happened, at 50p happened. So essentially I'm receiving these timed events and I'm giving verdicts true, false, currently true or currently false. So my monitoring device, which is a wearable device, can provide these verdicts at runtime by just examining the traces of my system. So for example, here is an example of that property P4. So if I receive at time instant 50p, then this transition triggers. That means I can still accept it. It is not a violation. At 208, I received R. It is still not a violation. I go to L1, but the outcome is currently true because you see that I'm in L1, but I cannot say that it's totally accepted because there is a possibility that I can go to L2. So the outcome is currently true. I cannot give a conclusive verdict as yet. Then at 300, I receive a P. Again, that's less than the RP interval, which is 900. So again, I say currently true. Finally, at 451, I receive an R. This value is less than 900. So I go to L2 and I output false. That means I can now sound an alarm. So the essential idea is that maybe the hacker has hacked and has altered the timing intervals on the pacemaker. As a consequence, there is a violation that the RP interval is not respected in my ECG. So I can either perform verification statically or I can perform verification at runtime. So just to conclude, in this talk, I presented the idea of emulation of human organs, which I think might aid the certification of implantable medical devices better. As a proof of concept, we have shown a kind of a cardiac conduction system of the human heart. I would say this is still work in progress. This has a lot of open-ended questions to be addressed. And I think as a proof of concept, we can show that we can scale to possibly thousands of nodes. Wei was talking to some biophysicists at Oxford who were talking about increasing the resolution of this conduction system much beyond the kind of 44 node network that we have. We have also done some work on kind of extending this work to kind of techniques where we have done some kind of piecewise linear approximations of the cardiac conduction cell using the concept of smooth tokens, and that makes things more scalable. In the future, we are going to examine other organs, modeling of autoarrhythmic cells, and personalization. That's all from me. Let me see if I can show that video, and you can ask me questions while I do that.
Thank you, Partha.
Thank you.
Very interesting.
Thank you, Vinod.
And we'll see if you can emulate or show us the, I guess the synchronization in the YouTube video. But in the meantime, questions for Partha?
Yeah. Let me see if there are questions first.
Go ahead.
If
Yeah.
you hack the pacemaker, can't you just program it as well?
Yeah, that is indeed a very, very good point. So the device that we have assumed has no wireless channels. So the idea is that the pacemaker is hackable because it has wireless channels, but the device, the wearable device, has no wireless channels. It is programmed once by the doctor with its timer settings and is not programmed again until the doctor decides to reprogram the pacemaker. So that's the essential idea. Yeah.
You are sort of testing the device by, I guess, hooking it up to what is assumed to be a good simulation of the performance or the behavior of the actual organ. That is a model, an approximation in itself. And there are many different models that you can choose from depending on the types of behavior you're interested in. You can't guarantee that this model is going to reproduce the entire set of behaviors that are likely to be encountered in a real heart. How do you decide whether the model is sufficiently complicated and able to reduce with sufficient fidelity, the behaviors that are likely to be seen? That seems to me a very, very important decision that I guess can lead to some dire consequences if the behaviors are not able to be reproduced and hence tested with your device.
Paul, thanks for the question. We are aware of this question, and we presented to Uniservices almost 2 years ago, and Mark True's response was that if we can detect a bug in the pacemaker, irrespective of the fidelity of the device using which we are testing the pacemaker, it's a bug in the pacemaker. So any bug that we detect is worth detecting. So that's the first response I will make. The second response I will make is that your question is a very, very interesting one, and it has always bothered me with this kind of work. So whenever we create an abstraction of any system, we have to actually show that it's a sound over approximation of the system. I think you are essentially hinting at that. By sound over approximation, what I mean is you have a concrete domain, you have an abstract domain. all the behaviors of the concrete domain are a subset of the behaviors of the abstract domain. For example, the random hat model that I showed you is a very good over approximation. It is very abstract, yet it can exhibit wide range of behaviors of a hat. And it is sound in the sense that it sort of encompasses all possible behaviors. Now, turns out that if I use such a model, I will, and use that to test my pacemaker, I won't be able to detect many errors. So essentially, the UPenn Heart-on-FPGA project used such a timed automata model to test pacemakers. What we do, on the other hand, is what Weiwei has been doing, is that she has this conduction system in MATLAB Simulink. She connects a pacemaker in MATLAB Simulink, and she has an AI-based algorithm which sort of induces different kinds of disease states in execution so as to move the cardiac model towards failure. And she shows in her work that this is a good way to find some problems with parameter settings of pacemakers. So what she shows, for some parameters of pacemakers, the cardiac model behaves normally, but for certain other parameters, the cardiac model induces diseases like PMT. So at least we can use this kind of methodology to decide the best kind of parameter settings for a given patient, for example. So I am not claiming, to answer your question, that the model that I presented is bulletproof. It is exactly identical to the bioengineering models. All I'm claiming is that it might help in giving more confidence to the design process of implantable devices. Did I answer your question?
Partly, yeah.
Right, so I was curious about one thing. So with the formal verification, you are essentially, I guess, mathematically proving that under all possible circumstances, the model or the pacemaker behaves as you expect it to do, so that there is not even a theoretical chance of failure. But I mean, I guess in practical situations, we would accept a small chance of failure when some certain rare conditions occur, because it may be completely impractical to say we want a device that would never fail no matter what happens. So how do you then the formal methods may then say that this design is not usable because it fails under certain circumstances. How do you decide if those circumstances are rare enough that you would be prepared to accept the risk of failure?
Yeah. So this is an intriguing kind of question, right? So what do you do, and what kind of failures can you accept, and what kind of failures are impossible to accept? So with formal methods, with kind of techniques like UPAL, there is an obvious problem with scalability. So you can verify the pacemaker working jointly with a random heart model, and you can verify certain timing properties, but you cannot verify once these models exhibit continuous phenomena beyond just time. So basically what Weiwei shows is that if you verify with just the random heart model, and if you use this random heart model in testing, you will miss number of behaviors. And it is essential that when you test in the closed loop, it is better to have kind of more detailed models. And she is able to show that through kind of, so we can verify some simplistic timing properties. We won't be able to completely prove, for example, the reachability problem of hybrid automata, that a given cell will achieve a voltage of such and such. If I want to do a proof like that, I won't be able to, because the problem is undecidable. Okay? So just to answer your question, this is the challenge faced by formal methods researchers. On one hand, there is the issue of scalability of verification. On the other hand, so to achieve scalable verification, you employ abstraction. So you miss out information, and you can verify the system, but then the kind of properties you verify are also limited. You cannot verify all possible properties. So what people do, to address your question more concretely, people combine formal methods and testing to increase the confidence of their approach. So this is called model-based testing. So you use formal methods, you use that to get some counterexamples, and these counterexamples can be used to derive better test cases, for example. So I cannot claim that formal methods is a solution, is a panacea for everything. Now in this work, also formal methods can be used to generate correct by construction code for certification. So that's another avenue that we can exploit for medical devices.
Any questions? Sorry, Amy, did you have one? No. Go ahead.
So you're able to apply formal methods to, prove the correctness of the logic of a device, at least at the software level. But there are also issues of, hardware failures. Logic gates might behave incorrectly.
Yeah.
Are you able to? Are the techniques able to be applied to cope with that level of problem occurring?
Yes, sure. Formal methods work very well for hardware. They work better for hardware than for software, and they scale way better. So basically, there are techniques like BDDs, and BDDs combined with SAT solvers have been used for hardware verification of very, very complex hardware. So hardware industry has been using formal methods for 20 years or more for verifying chips. Intel uses it, AMD uses it, pretty much every chip designer uses some form of formal methods. Basically, the technique they use is called equivalence checking, and equivalence checking is widely used. It's software verification which is more challenging. So I guess your question is, okay, I take this cardiac conduction system, or I decide to implement partly in hardware, partly in software. How do I ensure that the overall system is flawless? Now, this is a difficult question. Partly we can check it is flawless, assuming that the logic gates will operate correctly all the time. But to answer your question more concretely, we have to look at the reliability of the underlying logic gates as well. This is where safety standards come in. So what they do is they use techniques which are founded in reliability, like reliability block diagrams and so on and so forth, to see that the overall reliability of my system is within some tolerated bound, like you are asking. So their safety standards would employ techniques to see this. But formal verification will not be going into the reliability aspects.
All right, in which case let's thank Partha for a very interesting talk.
Thank you very much.
Copyright University of Auckland, all rights reserved. The content and delivery of lectures in this course are protected by copyright. Material belonging to others may have been used in these lectures and copied by and solely for the educational purposes of the university under license. You may record the lectures for the purposes of private study or research, but you may not sell, alter, or further reproduce or distribute any part of these lectures to any other person. Failure to comply with the terms of this warning may expose you to legal action for copyright infringement by the copyright owner and/or disciplinary action by the university.